Hey folks, want to do a video to gauge interest in doing this celestial navigation stuff, sort of simulating doing cell nav while you're en route to your patrol zone, as well as on your way back from, so RTBing from your patrol zone. I don't think it's going to be too much, given the fact that we're really only doing the navigation simulation stuff to and from the patrol zone. So it's not going to be all the time, and it's at least something that can. It's interesting. At least I think it's interesting. Plus, it'll allow a few more things to do while you're waiting for a run to be generated. So uh, it's going to work a little differently in this case. I could change it to be more exact, more true to life as far as what a navigator would have done or would do. But we're going to simplify it a little bit, and we're just going to use sun sites, simulate using sun sites. So uh, we're going to use what's called a running fix. So typically, what a navigator would do using celestial navigation would be there would be really 5 sites during the day. So you'd have your morning round of stars and planets, maybe three to 5 lines of position to establish a good solid fix. Okay, and then in the morning, mid morning, you'd get a sun line, uh, and then you would advance uh, one of your morning lines of position to that sun line, dead reckon that line up essentially. It's called a running fix. So give you a fix, mid morning fix, and then you do the same thing at noon, or roughly at high noon. You'd get another sun line, do another sun site, and then you'd advance your sun line from the morning to that point, and then you would do an afternoon sun line, advance one from noon up to that, and then you would, in the evening, you would do another round of stars and or planets to get you a solid fix. So really, the solid fixes are coming at dawn and dusk, and the sun is really only used to get a running fix during the day. What we're going to do is we're going to leave the star rounds off of this and just do the sunline fixed stuff. So you can get pretty much ballpark accuracy doing that, and it avoids having to be too much work. Plus, once you get into your patrol zone, there's you're just assumed to be there, so it's almost like a like a safe area. When you get in there, you don't have to worry about where you are. You're always going to be guaranteed to be in there. So that being said, so what you'll be given is you'll be given something kind of similar to this. You'll have 3 sites, one in the morning, one at what's roughly high noon, and then one in the afternoon, and you'll have an HO figure. HO means observed height. It's essentially your sextant reading for of the sun at that particular time. Okay, so we are going to use, I guess preliminarily, unless people express interest in doing it the old school way, we're going to use a website to do the site reduction for you. So when I say site reduction, what that means is, back in the day, what they used to do is they had reams of tables that would do all the math for you. Before the advent of a calculator, before GPS, all that stuff, right? You needed to do the spherical trigonometry in some fashion, and that way was by way of table lookups. Okay, so I do have one of these open. Two things open. First is the Nautical Almanac. You'll need this regardless, but for those hardcore folks out there that want to do it the old school way, I'm not going to walk through this in this video. See me if you're interested in learning more about how to do it via table lookups. But anyway, this is more the old school way to do it. These huge, long, this file is 397 pages, and it doesn't even cover all the latitudes. Okay, so this table lookup stuff is something that's beyond the scope of this. We're not gonna do this. If you want to learn how to do it the old way, the manual way, just come see me, and I'll teach you how to do that. So that's Pub 229 site reduction tables for those that are interested. in that. So so that's that. And then, but the other one, the Nautical Almanac, you'll always need this, and I will post these up. So you'll have, this was actually created by a Silent Hunter player who several people devised a way to do celestial navigation with the Silent Hunter games using a planetarium software. So it's actually similar to what we're doing here. It's actually how I got the idea to do this, and I figure why not use his tables because his all of this nautical almanac data is all correct in here. So let's assume that we're on the 16th of November, okay, 1939. So we've got our 1939 almanac open. We're down to November 16th, and you can see there's several pieces of information here. All of which, not all of which, but some of which we're going to actually input into this site here. This is a good site. It's going to allow us to do the site reduction without having to do all the table lookups, etc. Okay, so let's reset this. Okay, so then we're not going to actually even use all of these fields because all of these are assuming, most of these are assuming you're actually taking a sextant reading that's subject to error and all these corrections. Be thankful that you don't have to do all that stuff. We're just going to assume that your sextant reading is the adjusted observed altitude and go from there. So that's that. You are all familiar at this point with the BdU map that we're using, aka Google Maps, for lack of a slicker approach. But anyway, so you're familiar with the plotting, how this works. So let's assume that we are at this position here, and this is our dead reckoning position. For purposes of this, it'll also be our assumed position. We can just use our DR position as our assumed position, okay? We do need to convert it to degrees, minutes, and seconds, though, which I'll go over. So that's that, okay? I do not recommend that you do your plotting in this map because you're going to need a way to draw azimuths, angles, etc. You could use this protractor tool that this is an add-on, a Chrome add-on, but what I'm actually doing is I'm actually going to use Silent Hunter 3, and I suggest you use Wolfpack. But since I'm running OBS Studio and recording this, me having all of these things open, including Wolfpack, causes a real strain on my system. So I'm actually going to use, for demonstration purposes, just use Silent Hunter 3, just so that you can see a map with map tools in it. It will be very clear to you how to translate what I'm doing into Wolfpack. There's no doubt about that. So first and foremost, I'll just plot what we think our dead reckoning position is right here. Okay, that's going to correspond to this here. Right. So that's that. We also said in our on our map, let's just assume that we're en route to our patrol zone, and we're steering a course of 318 degrees. So we're going to plot 318 degrees up here. Okay, let's just extend that line out, 318. All right, like this. Okay, so that's going to be our DR line. This is our assumed position here, and that's where we're headed. Okay, so that is that, and then I guess I can get that a little more exact. There we go. Okay. All right, so that's that. So now we're pretty much ready to do this. So a few pieces of information we need to put in. So the first thing we need to do is we need to get the Greenwich hour angle. What the Greenwich hour angle is the angle of the body, that is the sun in this case, from Greenwich, which Greenwich is obviously 0 degrees longitude. Okay, so what this section is doing, and the information you're getting from the Nautical Almanac here, is essentially the location directly under the celestial body that you're observing. So at our first site, which is assumed to be 0900, at 0900, the sun, if you were to go draw a line directly down from the sun to the point that it meets the earth, that point is at 318 degrees and 49.5 minutes west of Greenwich. This is always measured west of Greenwich in a circle. Okay, so going west of Greenwich, if we were to go 318 degrees around, boom. Okay, so essentially the sun is in the eastern hemisphere right now. Okay, that's what this is saying. Right. The value is declination. Declination is the latitude of the body, of that point straight down from the sun. Okay, so drawing a line straight down from the sun, where that line intersects the Earth, is at 18 degrees south, 18 degrees and 33.2 minutes south of the equator. Okay, so that is the what's called the GP, or the geographic position of the sun at this particular time. These are pieces of information we need to input. So 318.49.5. So 318 and 49.5 minutes. Okay, and then declination is 18.33.2. 18 degrees 33.2. Oops, and that's going to be south. Okay, so we have those. What we're trying to derive is the calculated height and the azimuth. Okay, so our handy dandy site will get us that information. So first, we need to put these things in here. So first thing we need to do, we need to put the Greenwich hour angle in. That's 318 49.5. 9.5. Good. Okay. And then the declination is 33.2, and that's south. Don't forget that, south. Okay, so we got that in there. Now we need our assumed position. That is our dead reckoning position. Okay, so we need to convert that into minutes and seconds. So how do we do that? Well, the Windows calculator has the ability, and I imagine the Mac calculator does as well, but it's this DMS, or if you invert it, it says degrees. That is how you convert it. So if we just type it in, 56.84907 degrees of latitude, we know that's in decimal degrees. So we press DMS, and it gives us the minutes and seconds. 56 degrees, 50 minutes, and 57 seconds. That's how that translates. So you'll always have to get a decimal value of the seconds. Of course, you need to divide that by 60. So 56 divided by over 60 is essentially 1. So you can just round this up to 51. 56 degrees 51 minutes. Okay, that's our assumed latitude. 56, 51 north. Good. Now we do longitude. It's pretty simple. 3.54451. Okay, so we need to get that's in decimal degrees. So we press decimal degrees, we get 3 degrees 32 minutes and 40 seconds, or 3 minutes 30 and 3 degrees 32 point, let's say 7 minutes. 3:32.7. So we say 3:32.7, and we are east. Okay, so we've got that. Ignore this. We're not taking an instrument reading. We're just assuming that the amount that's given here, 8 degrees 32 minutes, is in fact our adjusted sextant reading. So we say 8 for observed altitude. We say 8:32. Okay, this is all the information we need for the site. So we say reduce site. All right, so now we have a computed altitude, which is HC. So we go, HC is 8 degrees and 17.3 minutes. Okay, got that in there. And the azimuth is just rounded to the closest degree. So it's going to be 144 degrees. Okay, so the azimuth is 144 degrees. These are what we plot, and let's see how we do that. So the first thing we need to do is we need to get HO minus HC, because what's happening here is you have an observed height. This is the actual height of the body at your current location, and then you have a computed height. Okay, this is based on the assumed position. So the fact that these are different means that, of course, your assumed position is not equal to your actual location. So we need to plot an offset. So what we do is we just take one minus the other. But which direction do we plot it in? Are we closer to the body, or are we further away? Well, the simplest way to think about this is there is an acronym But the simplest way to think about it is just like when you're looking through the scope and range finding a target. The higher the mast height, apparent mast height in your scope, the closer you are to the target, right? So therefore, if the observed angle, height of the body is greater than the computed one, you are closer to the sun. That means you plot in the direction of the azimuth. The azimuth is pointing to the body, right? So you think of the azimuth as a bearing, like you say if you were doing coastal navigation, you took a bearing of a lighthouse, etc. That's essentially what that is. It's the direction to the thing you're sighting. Azimuth is 144 degrees. Okay, so because HO is greater than HC, our quote unquote mast height is greater. We are closer to the target or closer to the sun. Okay, if you don't feel like you want to remember that, ho mo to, HO more toward. That's an acronym you can use. So in this case, the math is pretty simple. You take 32 minutes minus 17.3. We know 14.7. That's nautical miles. Okay, a minute of latitude is equal to 1 nautical mile. Longitude is more complicated, of course, because that's true at the equator for longitude, but the further you get north, obviously, longitude lines are not parallel to one another, so the 1 minute of longitude is gets proportionally less than 1 nautical mile the further north you go. It's actually the cosine of the latitude gives you the actual, and we'll see that in a bit. So, so this is the offset. We haven't. So these two pieces of information here are what we plot: the azimuth and the offset. And since we know that the offset is toward the body, we're going to plot it in the direction of 144. So let's see how this works. So let's go into whatever you're going to use to plot. I'm using Silent Hunter 3. And see, I wasn't too exact on this, so let's fix that. Okay, there we go. So, let me just move that really quickly. All right, so we're going to plot 144 degrees. We're going to plot our azimuth, 144. Okay, and we're going to down here say 144 like that. Okay, and typically it's a good idea to extend it back as well a little bit in case you need to go away from the body. But since we're going toward, it doesn't really matter. So that's that. Okay. 144. Okay. So then now we plot toward we plot the amount of the offset. So we know it's toward because HO is greater than HC. So 14.7 nautical miles. Okay. Well, our map in SH3 is in meters, so we need to convert that. So there are 1852 meters, 1,852 meters in 1 nautical mile. So to convert it, it's pretty simple. Times 14.7, so 27.2 kilometers away. Okay, so we need to measure 27.2 kilometers down the azimuth line. 27.2 is, I guess I should have extended that a little more. 27.2. There it is. Okay, so I need to extend my azimuth line down. That's no problem. 144 right there. All right, so from this point, we plot our line of position. So the line of position is always 90 degrees, is exactly perpendicular to your azimuth line. So we plot the line of position like so. Right? You can really extend it out. So 90 degrees. So hopefully it's clear how one would do this in Wolfpack using the tools in that game. So there we go. So that's the line of position done. So we can clean up the map a little bit. We don't need this. We don't need the azimuth line anymore. So now, what this is essentially what a line of position represents is a segment of a huge circle. So when you sight something, we sighted this thing, the sun, 8.5 degrees above the horizon. Well, that could be 8.5 degrees. That could be 8.5 degrees in any direction around 360 degrees. So therefore, technically, our line of position, is a huge circle. Anywhere on which we could be at this particular moment. But so technically that's not a straight line, but because the circle is so large, and we're using such a small portion of it, segment of it, it approximates a straight line. So therefore, in celestial navigation, you always use just a straight line to keep things simple. Straight line for a line of position, but just know that it really is a segment of a huge circle. And where those circles intersect is a fix. Okay. So that's our line of position. Okay, so that's our 0900 line of position here. All right. So at this point, what we're going to do is we're going to actually dead reckon our position up. Well, first of all we need to figure out what's called an EP, an estimated position. Okay, so we need to modify our DR plot now by this information that we know. So the best estimated position is the one that the line of position crosses your DR line. Okay, so that's here. So we're going to say that that's our new estimated position, and then we're going to dead reckon using 6 knots up to 2.5 hours later, which is the time of our next sight. All right, so we know that. All right, so we're going to hang on to this, and then we're gonna dead reckon our way. We won't plot anything on the final map until we're done with this whole exercise. Okay, so we're gonna plot from here all the way up our DR line, essentially to our next spot. So we can actually get rid of this mark here. That was our assumed position there. This is our new estimated position. So looks like we didn't quite make it as far as we thought we would. And that's a function of, in Wolfpack BdU, is just a randomized, call it like set and drift, if you will, randomized. So that's not because we were somehow inaccurate or anything like that. It was just that was based on the randomized error that's inherent in our navigation system in Wolfpack BdU. So let's use 6 knots, 2.5 hours. So we take 2.5 times 6 times 1852. So we're going to go 27.8 kilometers up in 2.5 hours. So let's plot that. 27.8 is going to get us 27.8 right there. So that's going to be our new assumed position for our next site. Okay. All right. So that's good. We got that. Now what we're going to do, we're going to plot another line of position here, but then what we're going to do is we're going to actually advance this line of position up to this assumed position here. We're going to dead reckon this up as well, and then we're going to see where those cross, and that's our running fix. All right, so the second one, the noon site, high noon site, is going to be pretty much a horizontal line, because really what you're getting at a noon site is you're sighting the sun when it's at its highest point, or very close to its highest point. That's going to give you actually a latitude, because if you think about it, that the sun is directly south of you. It's assuming you're in the northern hemisphere. At that moment, when the sun is at its highest point, you are directly north of the sun. So you are on the sun's longitude. You're on the sun's Greenwich hour angle. GHA is 360 degrees at that point. Okay, so really it's just math to derive your latitude, but we don't have, you see me if you're interested in how to figure that out manually, but I'm not going to go over it in this video. But suffice it to say, one of the advantages of doing a noon sight, high noon, is it's simple addition and subtraction to actually get your latitude. In fact, the old timers, old timers before this, the spherical trigonometry aspects were known. What they used to do is they used to use, that's how they used to navigate. They would just take um, sights of the North Star and sights of the sun at noon in order to get a latitude number easily, and then they would sail down to a particular latitude line, and then they would just sail west or east, directly west or east on that latitude line the whole time, just taking sun sights and North Star sights and getting a simple latitude. And then if they were too far north or too far south of that intended latitude, they would just sail up to it or back down to it again. But that's how they would do. They would sail on the parallels, so to speak. So anyway, but we don't have to do that now. But that's going to be a relatively horizontal line in here. Okay, so let's just take that site. We'll plunk our information in. But what we need to do first is we need to actually get what our new assumed position is. So we said that that our position was a little bit off. Okay, and you know what? I should have probably measured that, because we're going to need to know it to plot on the map. But at any rate, we can actually figure this out. It's actually not very hard. So what we can do is we need to convert this into a longitude and latitude, new longitude and latitude number for our assumed position. Okay, so the way we can do that is to simply say we knew what our assumed latitude was here, or I guess where we originally plotted it. So we need to figure out what the amount was, our offset was, which we know was 14 miles. All right, and then we need to plot from there up to our new assumed position, which is where we're going to plot our next one. So so I think the easiest way to do this is actually to let me think about this for a second. We could plot it either on the map itself, which might be easier now that I think about it, or we could simply derive it from this, because we knew what the original one was, so we would need to figure out what the offset was, and then go from there. Or you know what? Now that I'm thinking about it, I think it might be easier just to do it in our map. So what we'll do is let's just say we knew our offset was 14.7 nautical miles. Okay, so that was the difference between our original DR position and where we just plotted it. That is going to be in statute miles, 14.7 times 1.15, about 16.9 miles. Okay, so I shouldn't have been so hasty in deleting this tick mark up here. That's my fault. But let's just say this 16.9 is going to be close enough. Okay, so 16.9, and then we're at 318 minus 180, 138. So let's actually go into our instead of having to try to figure out the latitude and longitude in the map here to try to convert it, we can just simply use it on the map, plot it on the actual map itself. So because we don't have those marks in here, so 16.9. So what we're doing now is I'm going to use this, and I actually maybe suggest you do get your hands on this protractor tool here. Or some sort of protractor tool, so you can measure angles. But what I would suggest you do is just make a line and update your new DR position, in here. So like this. Yep, save it. Okay. And then 138. So we're going to measure 16.9 back from there at 138, which is about right there. It's close enough right there. All right. So then, oops. Yeah, there we go. All right. So that's going to be right about there. Okay. So then we are going to get 16.9 from here, and then that'll be our new DR position, 16.9 right here. Okay, so then that's that. So then let's just lay down a mark right here. Okay, so that's our new estimated position. Okay, right there. All right, so now we're gonna, from that point, we're gonna dead reckon up, up to our new spot, which is going to be, 2.5 times 6 times 1852, 2778. But since we know it's 6 nautical miles times 2.5 hours is 15, it's going to be 15 nautical miles times 1.15 for statute, so it's going to be 17.3 statute miles. So let's just measure that, and that's going to be actually our new our dead reckoning position, 17.3. That's actually pretty close to what our original was. 17.3. Okay, right there. All right, so then that's going to be our new DR. That's going to be our new estimated position. So in fact, let me update update this to come up here. Okay, so that's our new estimated position at 11:30. Okay, at 11:30. Right. Okay, so we're good there. Right. Yep, I won't be so hasty in deleting the tick marks here next time. But anyway, so that corresponds to this. Okay, so now what we're going to do is we are going to do the second site. So we know it's at 11:30, and at 11:30, our observed height is 14 degrees and 40 minutes. Okay, so we need to get GHA for the second site. GHA, it's at 11:30. So we say now we have an issue here, right? Because we're halfway between 2 hours, so we actually need to interpolate, and that's actually not very hard to do. So the sun moves 15 degrees every hour. Okay, so knowing that, you just know that's that's the difference between each one of these lines. So in our case, if it's where we took the site at 11:30, half of 15 is 7.5. So that's pretty straightforward. So what we would do then is we would add 7.5 degrees to this figure here. So let's convert that to decimal degrees. So we'd say 348.4918, which is 0.3, and then we say that's a degree, so that's a decimal figure there, plus 7.5. Okay, 356.32. Let's convert that into degrees. 356 degrees, 19 minutes, 19.3 minutes. So we put that's our GHA. So we go in and into our website, reset 356. So you can see Greenwich hour. We're almost on the meridian of the sun. Not quite. We're not quite at local high noon. We're pretty close though. All right, 356, 19.3. Okay, 19.3. All right, the declination at that time. Again, we're going to have to interpolate. Between 11 and 12, it doesn't quite move as much. Okay, so 18 degrees 34.5 minutes versus 35.1. Okay, well I know that that change is 0.6 minutes, so half of 0.6 is 0.3, so 34.5 plus 0.3 is 34.8, right? 18 degrees let's say 34.8 south, don't forget that. Okay, now we need to put our assumed position in. Just plotted it, the map that's here. Right, so we need to convert it to decimal to whole degrees for the website, so we say 56.85405. That is a decimal figure. We need it in degrees, so that is 56 degrees 51 51.3 56 no 0.2 56 51.2 56 51.2. All right, 56 51.2, and then longitude we convert it. We say 3.53576. Convert that to degrees. It's 3 minutes, 3 degrees 32.1 minutes. 332.1. Okay, 3.1. Okay, and that is east. So we got our GHA in, we got declination, we've got longitude, latitude of our assumed position. We put our observed height in, which is 1440, and we compute the site. Okay, so HC computed is 1434. Oh, I didn't fill this in with GHA and declination, but you saw what that was. 1434, and then the azimuth is was just rounded up to 180. That's close enough. Okay, 180. So we're pretty much, it was pretty close actually to, I was wrong. It was actually pretty close to high noon. High noon is, it's going to be, the azimuth is going to be 180. Okay. Let's just round it to 180. All right. So you can already see how it's going to be a horizontal line, because the line of position is going to be perpendicular to the azimuth. All right. So let's plot that. All right. So we can plot that, and we say we need an azimuth of 180. So that's pretty straightforward. So like this, 180 right there. Okay, and then we need to convert. We need to get HO minus HC, the offset. Okay, so what's bigger? HO is bigger again, so it is toward. HO is 1440 minutes, 14 degrees 40 minutes, and the HC is 14 degrees and 34 minutes. So you can already see that we're 6 nautical miles, the difference between 40 and 34 there, 6 nautical miles toward the 180. So we need to convert that to 6 times 1852, 11.1 kilometers. Right. .1 right there. Okay. All right. So then from this spot, since we plot a 90-degree line of position. Okay. So we do right here. We come down here. Okay. We plot a line of position that's perpendicular to that. So you can see that it is pretty much horizontal. Okay, let's just extend it back the other way. Right, just like this. There we go. Okay. Boom. Okay, so that's our next LOP there. All right, we can get rid of that. Get rid of the azimuth. Okay, so now what we do is we advance our line of position from here up to here. We need our first line of position. So the easiest way to do that in this, I know we have the parallel lines now in Wolfpack, but in order to do this in Scion Hunter 3, you actually have to do a circle and then just move it up. So we'll do that now. Simply take that and then move that up here. Okay, so you can see, okay, right there. All right, so then the line of position, and I actually need to extend this now. There. Okay. So, you can see, we've got based on our running fix, you can see there was actually a little more error in there than we thought there was. Okay, so this is our new updated position here. This is a running fix right here. Okay, our first running fix right there. All right, so let's first of all, in order to plot on the map, let's figure out what direction we need to go in and what distance. So let's go ahead and figure that out. So we actually need to go to plot this. We need direction of 234 at 18.9 kilometers. 18,900 divided by 1852 times 1.15 is 11.7 miles. Okay, at what did I say? 232, I believe. 234. 234. Whoops. 234 at 11.7. Alright, so let's just plot that updated fix. 234 at 11.7. Alright, let's do that, and then we do 11.7. Be about here. Okay. Oops, wait. I need to get the angle. Excuse me. 234. There's 234 right there. Thereabouts. Okay, we need to get the line, and then move the line over right there. Okay, there's 234. Just like that. Okay, and then we go 11.7 from that point. Okay, so 11.7. 11.7 is right here. Okay, that's good there. Okay, and then then we'll plot an updated fix right there. Okay, so that's our that is our new assumed position. Okay, so you can see we were from a miles perspective, we were 17 miles off. Okay, so 17 miles off. All right, so that's that. That error will get better the more check rides you do. Okay, that's the type of error that's being generated by the check rides. Okay, so that's fix number 2. So that is where we're actually going to move our estimated position to right there. Okay, and then we're going to start our plot from that point there. So let's get rid of this. All right, so then that's our updated fix. We're going to keep moving up based on that. So let's just assume we're going to keep going on 318 degrees. We want to keep this line of position. Don't delete that. Delete that line, but we can see you don't have to keep this one anymore, but you can if you want to. This we need to keep. Okay, so let's plot another. So how far are we going to go now? So we're at 1130, and we want to get to 1400. So that is again 2.5 hours. So I've forgotten 2.5 times 6 times 1852. Okay, 27.8 kilometers. That's what we're going to travel. Let's just assume the same course, okay, just for argument's sake here. 27.8. 318 at 27.8. Right there. Okay, so that's about right there. Okay, so that's going to be our new DR position right here, assumed position for our next site. And then we're gonna advance this up here for another second running fix. Okay, so we can delete this. It's not our course line anymore. This is our course line right here. All right, so let's go ahead and plot the last fix. So we know 1400 HO is 826. First, we need to get the Greenwich hour angle. Again, we're working with a whole hour again here, so it's going to be pretty easy. 14 Greenwich hour angle is 3349.1. 33. Let's reset it. 3349.1. And then we know the declination is going to be south again. That it's going to be 1836.4. Okay. There we go. We need to get the position. So that's going to be, again, we need to convert it. 56.75856. 5645.5. 5645.5 north, and then latitude longitude 3.28241, 3 degrees 17 minutes. 3 degrees 17 minutes. Okay, so we got that. We got this in. We need the observed altitude, which is in this case 8 degrees 26 minutes. 8:26. We reduce the site. Okay, it's 8 degrees 28.9. 8 degrees 28.9. Okay, and then the azimuth is let's just round it down to 215. Okay, 215. All right, so again we compare HO to HC. All right, just like that, and then that's going to be what's bigger. In this case, the computed height is actually bigger than the observed height, so we're actually further away from the body than our assumed position. So instead of 215, it'll be on the other side of the assumed position from that. So, but we can figure it out. We can just do the math, just how we did before. Minus 28.9 minus tells us it's away. Minus 2.9 nautical miles. Okay, so then we need to convert that into meters. 2.9 times 1852 is 5.4 kilometers. All right, so first we're going to draw our azimuth of 215. Okay, azimuth of 215. So we do that now. But then we're going to extend it back the other way. Hold on here. Okay, azimuth of 215. Okay, 215 is here. Okay, but then we're going to extend it back because it's away. Right? So, okay, so then we said 5.4 kilometers. So then we do our, we measure our distance. 5.4 kilometers right there. All right, perfect. And then we're going to get our line of position from that. Okay, we're going to draw an angle of 90 from that point. and that's going to give us our LOP. Okay, so then we've got that, and then we draw that over here. Okay. Just like this. Alright, so that's our third lineup position right there. Alright, let's do our cleanup. We don't need this. We don't need this. Okay, so now what we do is we advance this this line up to the new dead reckoning position. We'll see where these intersect. Okay, so that's the next step. So this is the next running fix. So to do that, we get our movable circle here. Okay, the same, much like this, and then move it up here. And then you can see we need to extend the line of position. So to do that, the safest thing to do is to just do this. Okay, like that. All right, so then that right there, this is our new fix right here. Okay, so that's our new fix right there. So we can we'll keep these two so that we can figure out how much to move our marker by in our true map, and then this will be our final for the end at the end of the day. This is our final position, so we'll see where that ends up. So let's just measure real quickly. Again, this is just to update our map. So it looks like we were basically straight east, 9.3 kilometers. Okay, so 9.3, which is 9,300 divided by 1852 times 1.15 is 5.8 statute miles. Okay, so 5.8 statute miles directly east. And then let's do this. Okay, and then so directly east is going to be 90. Pretty much spot on there. Okay, so then right there. Okay, so that's good. And then we said the distance was going to be 5.8. 5.8. So then 5.8 is going to be here. That's close enough right there. Okay, so then we're going to update that. So that is actually our new here we're going to move our boat here. Okay, so that's our new position, our new fix right there. Right. So this we can delete. All right. So then that is our final. That would be our final fix for the day. Okay, that would be our final fix for the day. And then that'd be pretty much it. So that is it's right here. Okay, so that's our last line of position right there. Hang on to these lines of position, the last one you plot, because you never know when you're not going to get a fix, not going to be able to get a sun line. Okay, as you're doing this, so always make sure you hang on to your most recent LLP so you're able to advance it as need be, in case you can't get a sighting. Okay, so that is that. So then I'm just going to make a note of what our final position was. 5675. Yeah, 75837343416. Okay, so then, yep. So 56. Just make a note of that. 75837 and 3.43416. Okay, so that's that. Yep. Okay, and then It's going to be off. It's not going to be super exact, because from your dead reckoning position anyway, because of the randomized error. But at least it gives you an approximation of where you're going. And there might be a little error in this, by the way, because of the fact that I deleted that first dead reckoning position. That could have introduced a little error, but the point is you see how it works in here, and you see how the how things are plotted. Like I said, I recommend you do your days plotting in a software such as this, whether it's Wolfpack or Sound 3 or whatever, just so you're able to get the tools in here. But you could also do it in here if you use some kind of a protractor add-in, and you can plot all your lines just in this map too if it's easier for you. So that's either way. But again, this saves a lot of the work here. I would recommend that everybody use this for starters, and then if you feel like you need to, if you're bit by the immersion bug or whatever, and you want to use the old school ways, then I can certainly teach you how to use these site reduction tables if need be. So that being said, it seems a lot harder than it is. Once you get the hang of doing it, it's not that difficult. Particularly when you're using this website to do it, it becomes almost second nature after a while. And keep in mind too that this is for those of you that have a patrol grid that's here, for example, that's going to take you maybe 2-3 days to get up there. Okay, so and that's probably real life days, because it's with the back and forth between you and me. You're gonna, especially with time zones, you're gonna say, hey, Stas, I updated my position. Send me a radio message or whatever, and then I'll go in there when because I have a full-time job, etc. When I get to it, I will go in um, um, and update you. But I would, in this case, I would give you your sites for the day, and you would say. So what you would really do is you would plot up until like a 9 a.m. position, okay, and then I would get, once you plotted that 9 a.m. position, I would give you your 9 a.m. site, your noon site, and then your afternoon site. And then and then you would plot your way up that, and then to get us to 1400, and then from 1400 to 09 again, you would be just running on faith essentially until you get to the next day, right? And then you can do your plotting again. So I guess long story short, watch this, study this, or just give a preliminary yay, nay, no, this is too much, or yes, this is great. And also, bring me any ideas that you think that would, because I'd like to, it'd be nice to keep this concept in some fashion in here. But if there's opportunities to simplify this at all, also please let me know of those too. So that being said, I will call it a night, but thank you. And yeah, just please, this is going to be a working discussion, so let me know what your thoughts are. All right, take care. Bye.